alkaline again, right? So the estrogen receptor binds to beta estradiol, it releases beta estradiol after some time. We'll see how receptors work later on in chapter 12 and 13. But enzymes also have to bind their substrates, but now something else happens. Once the substrate binds to the enzyme, obviously, the substrate changes, right? And how does it change? Well, what enzymes do to the substrate is that they catalyze a reaction. That substrate is a cardinal, right? So it could be an isomerization reaction, it could be a free transfer reaction between two different substrates. We'll get to that later on today. But what they do is to catalyze the reaction. And if you remember, right, what is a catalyst? A catalyst just makes a reaction proceed forward more quickly, right? It increases the rate of the reaction. But it doesn't change whether or not a reaction will proceed, right? What determines what if a reaction will proceed, right? A reaction or process. What determines if it's going to go forward? Delta G, right? So delta G is what determines if a reaction goes forward. If it's negative, it proceeds. If it's positive, then it's not favorable, right? And catalysts cannot change this, and neither can enzymes, right? So for example, right, here we have some enzymes, some example enzymes, and what we see, right, is the rate of an uncatalyzed reaction. So for example, carbonic anhydrase, which is one of the most catalytically perfect enzymes that we know of, catalyze the conversion of CO2 into HCO3 minus, right? Carbonic acid or carbon, right? Hydrating CO2. In reality, right, if we just bubble carbon dioxide through water, okay, this has got a rate constant of about 1.3 times 10 to the minus 1. Now in the body, this is insufficient, right? We don't want carbon dioxide dissolved as a gas. We want hydrated carbon dioxide. We transport it out into the lungs and then turn it back into carbon dioxide to breathe out. We don't want dissolved CO2 gas in solution. So we need a way to convert CO2 into HCO3 minus at a faster rate than would happen on its own. All right? And this is where carbonic anhydrase comes in. Look at now the catalyzed rate. It's 1 times 10 to the 6th per mole, or per second rather. 1 times 10 to the 6th. So we have a 10 to the 7-fold enhancement in the rate of the reaction. Again, this won't change that the reaction will proceed, okay? But it just makes it happen faster. We'll see the mechanistic reasons for that later on. All right, so enzymes, like receptors and their ligands, have to be specific for their substrates. You can't have enzymes going around interacting with anything. So they have to be specific, they have to catalyze specific reactions, and they have to involve specific substrates, right? So a specific enzyme catalyzes a specific category of reaction on a specific substrate. We see different categories of reactions later on here. The level of substrate reaction specificity can vary, though, between different enzymes, even enzymes that catalyze the same reaction. So for example, proteases, right? We're talking about different classes of enzymes. Protease is an enzyme that breaks down or hydrolyzes a peptide bond. Remember, a peptide bond holds 2 amino acids together in a polypeptide. A protease just breaks this apart using water. It's a hydrolysis reaction, right? And that's what we see at the top here. We have a peptide bond plus water yields now 2 amino acids, all right? And now we've lost water because the water is now incorporated into the 2 amino acids. This reaction will proceed forward. It's got a delta G of about negative 15 to 20 kilojoules per mole, depending on the circumstances. And so it will proceed forward. And this is what's catalyzed by proteases. Now, if you look at the structure of an ester, right, on the bottom, an ester looks kind of similar to a peptide, right? Looks kind of the same as a peptide. And what we see is that if we do the same reaction, we can hydrolyze an ester into an acid and an alcohol that you see on the right there. Because they look so similar, proteases are also known to hydrolyze ester bonds in addition to peptide bonds, right? Not as well, but they can do it. So the shape of the substrate determines the specificity of the enzyme, right? And as we'll see, it's the shape of the enzyme that determines the specificity for the substrate. They fit like a lock into a key almost, right? Now, what stops this from happening, haphazardly? Why is it that an ester bond is hydrolyzed less frequently than a peptide bond by a protease? Right? Well, again, it's based on shape complementarity and weak forces, right? Remember, everything comes down to the shape of these different molecules. So the shape of the substrate has to match the shape of the active site of the enzyme. And how do we maximize that interaction? With weak forces, right? Hydrophobic effect, hydrogen bonds, ionic interactions, right? So the shape of the active site is designed, just like we saw with the estradiol receptor, right? The shape of the active site is designed such that it maximizes the number of these weak interactions that are formed when the correct substrate is present, right? Here we have two examples. We have trypsin and thrombin. They're both proteases, okay? And so they both cleave the peptide bond, but specifically trypsin will cleave the peptide bond after a lysine or arginine, okay? Whereas thrombin only cleaves after an arginine, right? So what's going on here? In the active site of trypsin, the amino acids in the active site, we'll see an example of an active site later, the active site has residues that are able to form good interactions with either arginine or lysine, right? They're at the correct distance away, they're in the correct three-dimensional position, such that when there's a peptide bond next to a lysine or arginine, that maximizes the number of bonds, and so we get better binding between those, right? If we look at arginine, or rather thrombin, thrombin has a similar active site, but it lacks the amino acids that also make good interactions with lysine. And so thrombin is specific to arginine, right? Or specific to peptide bonds after arginine. So specificity can be multifaceted, right? We can be specific for one substrate, or we can be specific for several substrates. It depends on the structure of the enzyme itself. Now, what types of reactions can be catalyzed by enzyme? We can break down enzymes into 7 different categories. We have oxidoreductases. These catalyze redox reactions. And very often, a telltale sign of a oxidoreductase is that it will have the name dehydrogenase. For example, lactate dehydrogenase would be an oxidoreductase. It's going to reduce NAD plus into NADH while it oxidizes lactate into pyruvate. We have transferases. Right? Notice all these names end in aces. That's usually what enzymes name end in base. So transferases catalyzes group transfer reactions. So for example, kinases. Kinases are a class of enzymes that transfer a phosphoryl group from usually ATP onto some other molecule. So for example, hexokinase is going to transfer a phosphoryl group from ATP onto glucose to generate glucose 6-phosphate. So that's kinase. Hydrolases, like we saw, proteases are a type of hydrolase. They catalyze hydrolysis reactions using water to break something apart. Lyases add or remove groups to form double bonds, right? Fumarase in the citric acid cycle is an example of a lyase. Okay, don't worry about memorizing these specific examples here. We're going to talk about all these as we go throughout this semester. Isomerases catalyze isomerization reactions. Triose phosphate isomerase, TPI, is an example of that. Ligases ligate 2 molecules together, right? They put them together. And lastly, translocases move molecules across a membrane, like, for example, the sodium-potassium pump, which you'll cover with Dr. Barber later on. Right, so some enzymes also require cofactors. Right, and a cofactor is basically similar to a prosthetic group. Right, we've seen a prosthetic group already. In what protein? What protein that we've talked about has a prosthetic group? Myoglobin and hemoglobin. What's the prosthetic group? No, that's iron. Heme, right, which contains iron. And we can break cofactors down into 2 categories, right? We can have a coenzyme or a metal, right? Coenzyme is usually derived, or actually always derived from a vitamin. And we have some important ones here, okay? Somebody asked me before class, do you have to memorize the cofactors and their enzyme? The answer is no, all right? That would be pointless for you to memorize because it would make no sense. So right now, you don't have to memorize these, but throughout the semester, as we go, you're not going to have to memorize these because they'll make more sense in the context of the reactions that those enzymes are catalyzing. So for example, flavin adenine dinucleotide and nicotinamide adenine dinucleotide, FAD and NAD, these are electron carriers, right? So of course, they participate in redox reactions like pyruvate dehydrogenase or monoamine oxidase. Okay, we have thymine pyrophosphate. This is present in pyruvate dehydrogenase. hydrogenase, which we'll also talk about. All of these, right, Biochem, which carries carbon dioxide in many different reactions, like pyruvate carboxylase, these all require these coenzymes. Without these coenzymes, the enzymes wouldn't be able to catalyze the reaction, just like hemoglobin wouldn't be able to bind oxygen without the heme prosthetic group. Any enzyme that requires a coenzyme or cofactor must have that cofactor in order to function. We can also have metals, right? Metals can serve as a cofactor. Magnesium and manganese. It's here. Manganese and magnesium 2+. These are usually found in enzymes that deal with nucleotides or deoxynucleotides. They will almost always have a magnesium as a cofactor. The reason being, why? Right? Somebody else tell me. Why would an enzyme that deals with nucleotides require magnesium? What do you think?
Could it be that in order to stabilize the negative charge of the phosphates?
Exactly, right? Remember, what does a nucleotide look like? We have our sugar with a base, but we also have three phosphates in the case of a nucleotide triphosphate, like ATP or GTP. Each one of these carries a negative charge. Having magnesium as a cofactor helps to stabilize these negative charges and increases the weak force that brings those two together. Right? Another example of maximizing the weak forces. All right. So now moving on to the mechanics and the enzymology of enzymes, right? The kinetics. Okay. Well, let's go over again some basic stuff. A reaction will proceed when, somebody said it before, only if the Gibbs free energy change is less than 0. That means that the substrates have more free energy than the products. Right? So if we draw our reaction coordinate diagram here with energy on the y-axis and the reaction coordinate on the x-axis, we can look at this vaguely as time. All right? We always start with some substrate, right? With some, A. If we say our reaction is A yields P, right? Well, A will have its own characteristic Gibbs free energy. Every molecule has its own characteristic Gibbs free energy. Not a delta G, just a G. Right? So here we would say, all right, whatever that is. Now our P is another molecule. That also has its own characteristic Gibbs free energy. Right? So the change between these two is our delta G. That's the change in free energy. And of course, we know that the lower in energy a molecule is, the more stable it is. So between these two, which one is more stable? Which one's going to want to exist more? A or P? P, right? It's less energy, it's more stable. So will this reaction proceed forward? Yeah, right? So we can say that delta G of a process or reaction is the free energy of the products minus the free energy of the reactants. In this case, because the free energy of the products is lower than the free energy of the reactants, A, then delta G must necessarily be less than 0. Okay? Now, if a reaction proceeds forward, depends on delta G. But what we'll see more often is not delta G, the actual change in free energy. All right? It's the standard change in free energy, delta G naught prime. Right? So, why is this important? Okay? When chemists started doing all this characterization, different chemical reactions and different molecules, all right, it was important that they had a standard condition so they could communicate. That way they didn't have to, account for changes in temperature or changes in pressure. Like that. So, standard conditions was agreed to be, everything in solution has to be at 1 mole. Everything in gaseous state has to be at 1 atmosphere. Okay? And the temperature has to be 25 degrees Celsius, which is 298 Kelvin. Okay? Usually we just ignore the 0.15, but technically, yeah, 298.15 Kelvin. 298 rather, 298.15 Kelvin. So what is the prime here? So that's our standard free energy. Now, the prime means that it's also at pH 7, right? And what this means is that we can now ignore pH plus concentration. Okay? We don't have to take that into account, so So in any delta G calculation, we can ignore H plus, which makes our life a whole lot easier. So when we see a standard change in free energy, we know that it's under standard conditions. But in the body, in the cell, there are no reactions that are happening at standard conditions, right? For several reasons. What's one reason that in the body nothing is happening under standard conditions? How much? What's the temperature? 37, right? 310 Kelvin, right? So that's already not. What else? What else is the standard? Our stomach acid is way more acidic. Yeah. So reactions that happen in the stomach are actually a whole different area. One other thing. Homeostasis in general. Okay, sure, but also 1 molar is just a super high concentration of anything, right? So, you know, it was easy to define 1 molar as 1 mole per liter, but physiologically, 1 mole is a lot of stuff, right? So we're usually dealing in units of millimolar or sometimes micromolar, right? So we're not going to have anything going on at standard conditions. What we do have is the actual change in free energy. And it's the actual change in free energy, delta G, what we see on the right here, what that determines if a reaction will proceed forward, right? Delta G naught prime doesn't predict anything except for at standard conditions. If we have something other than standard conditions, then we need the actual changes in free energy at those conditions, which equals RT, or delta G naught prime, plus RT ln concentration of products over concentration of reactants. Now, if delta G, the actual change in free energy, is less than 0, that process under these conditions, so at these concentrations and at this temperature, there it will proceed forward. If it's positive, then it won't proceed forward. So what we care about in reality is not delta G naught prime, it is the actual change in free energy. That takes into account, again, both the temperature and the concentrations of our products and reactants.
But in the calculation, right, so if you have like two amounts of C that are quantum, usually the concentration is squared.
Yeah, of course. Yeah. So this is just, we can rewrite this to say that this is really, officially, right, Q. Right? And in that case, yes, of course, you have to take into account the stoichiometric coefficient. So, right, if it was A plus B yields 2C plus D, then C would have to be squared. Right? Remember that from Gen Chem. All right? So, what is the relationship between the equilibrium of a process, or the equilibrium of a reaction, and the free energy of that same process? Well, at equilibrium, delta G equals 0, necessarily, because what's going on at equilibrium? What's happening at equilibrium?
A balance of products being made and reactants being reverted back.
Right, so in our example here, A is being turned into P at the same rate as P is being turned into A, right? So what's happening? Right, nothing's happening, right? The concentrations remain the same. We're at equilibrium. Doesn't mean that nothing's physically happening, but in terms of the state of the system, it remains the same. So no energy now is available, so delta G is necessarily 0, right? So at equilibrium, 0 equals delta G naught prime plus RT ln Q. But at equilibrium, what do we call Q? Huh? Who said that? Equilibrium constant. Now, how do we write that? It's K EQ, right? So there's a lot of K's we've seen so far. This is a new one, K EQ. So we rewrite this. We say that delta G naught prime equals negative RT ln K EQ. But again, this is at pH 7, so we put the prime on our K EQ, so this becomes K prime EQ, right? So now we have a defined relationship between free energy and K prime EQ. So let's go back to our free energy diagram. Okay? An enzyme, remember, catalyzes a reaction. So does it change what A is? No, does it change what P is? This process will continue just faster. So if A is still A when it's enzyme catalyzed, does this change? No, right? The energy of A is still going to be A, and the energy of P is still going to be P. So does the delta G of a reaction change whether it's catalyzed or uncatalyzed? No, it can't, right? Because remember, delta G equals G products minus G reactants, and because neither of those is changing, then delta G necessarily is exactly the same whether it's enzyme catalyzed or uncatalyzed. Now, if we come over here, right? If delta G doesn't change, can K prime EQ change? Well, let's go through all of the factors here. Delta G naught prime, right? That's not changing. Can R change? No, that's a constant of the universe, right? So that's not going to happen as long as we don't transfer into a new dimension. T, is that going to change? Well, it could, right? But we're doing this at the same temperature. Okay? So the only thing left is K prime EQ. But if delta G isn't changing, R isn't changing, and T isn't changing, then K prime EQ also can't change. So what does this mean for an enzyme catalyzed reaction in terms of its equilibrium? This side of the room has been awfully quiet. What does that mean in terms of the equilibrium of this reaction? It doesn't change, so then what is an enzyme doing? It speeds it up, so what does that mean in terms of equilibrium? If that's not changing. Right, equilibrium is just reached faster, right? So it increases the rate of the reaction, and it gets to the same equilibrium it would have before, just faster. And that's what we see here. Okay, enzymes alter rate and not equilibrium. So here we have, for example, an enzyme uncatalyzed reaction. It's a normal enzyme. The amount of product being formed per time. Okay, you see that we start off kind of linearly here, and eventually, right here's where the double bars break. Eventually, we reach some equilibrium where the amount of product is now no longer increasing over time. If we look over here at an enzyme catalyzed reaction, right? Well, what's going on? We reach that equilibrium even before we get to the double break here, that double bar. So it's just shortening the amount of time that it takes to reach that same equilibrium. Now, interestingly, all right, this is going to be useful later on when we talk about Michaelis-Menten kinetics. We can also describe equilibrium constants, okay, using, yes, of course, the concentration of products and substrates, right? So P over R, like we said before, at equilibrium. But we can also define KEQ as the ratio of rate constants, right? So remember, if we're at equilibrium, that means that we must have some forward reaction, some reverse reaction with some rate constants. K is equal to P over S, but it's also equal to the ratio of the forward rate constant over the reverse rate constant, right? So in this case, Kf is 10 to the minus 4 over 10 to the minus 6, which is 100, right? So if we know the rate constants, we don't even need to know the concentrations of products and reactants. And this will be useful for us in just a minute, okay? Okay. All right, so how do these enzymes speed up a reaction, right? So in a chemical reaction, we can say that instead of going from S to P or from A to P, right? Really, we have to pass through the transition state, right? What is the transition state? So here, this is a bit of a simplification. Really, what we have is A yields this transition state, and then the transition state yields the product, right? So what is the transition state? Maybe remember what the transition state is. Yeah.
It's a high energy intermediate.
It's a high energy intermediate. Okay? That is correct. But what does that mean for us? It's high energy with respect to what?
Products and reactants.
Right, the products or the reactants. It's higher energy than both of them. Okay, so X double dagger, transition state is higher in energy than either A or P, right? And why does that matter? Where does the transition state come in here? Okay, sure. So we have to, there's a difference in the amount of energy that we need to put in to reach that transition state. But why do we have to reach that transition state?
So you get the lower energy product.
Right, okay? So we can't go straight down from here to here. Instead, we first have to achieve this transition state, right? So we have to put in some amount of energy. This amount of energy is the activation energy, okay? It's at this point now that we can determine which is going to be favored, the product or the reactant. Why? Well, now going from here down to here, okay, we're going to release also some amount of energy. If we're up here, okay, what's going to happen? We're going to go left or right. Okay. Which way are we going to go? More often. Which way are we going to go more often? To the lower energy. Why? Okay, but yeah, it's more stable. But look at this chart. Why are we going to fall down to the right? Because we could fall down to the left, right? We're at that precipice of energy, so we could collapse into either state. And the answer is what? What determines? Huh? It's going to be negative either way, right? Here, we're going to a lower energy. Here, we're going to a lower energy.
I guess it's a higher degree of spontaneity.
Yeah, but why? Right? Well, here, if we fall down, we can get back to A, but we can get back to X, right? So this is fine. Here, we can fall down to P, but we can also get back to X. But getting from A to P is easier than getting from P to X. So it falls down, and it can come back and then try again, right? And at equilibrium, what has happened is that enough of this has collapsed into both such that we have whatever the equilibrium constant determines there, okay? Now, the activation energy. This is what determines the rate of a reaction, okay? The higher the activation energy, the more energy that we have to put in to achieve the transition state, and so the reaction will proceed slower while we find that energy, or put in that energy, right? So the higher the activation energy, the slower reaction proceeds. This is why the hydrolysis of a peptide bond, okay, is negative, but proteins are kinetically stable, okay? We'll have an example problem on that in just a second. So, what do enzymes do? Enzymes essentially just lower the amount of activation energy needed, similar to all catalysts, right? And how is it that enzymes are going to lower the activation energy? Okay, so it changes the orientation of products and reactants, so it's easier to collide in the right way. But what if we only have one substrate?
When the enzyme binds, it creates these interactions, and the formation of these new interaction releases energy, and that energy is then used to lower that conversion.
So we're very close. It does have to do with creating bonds and weak bonds and the interaction between the enzyme and the substrate. But that was so close.
When you make those weak bonds, you release energy. That's it. And you use to
Okay, so let's say that we have an enzyme and a substrate, right? So it's a simple, we don't have two substrates or anything like that. We're just taking A and it yields P, okay? So you're saying we've got the enzyme, and that's gonna bind with A, and that maximizes the interactions, right? So if that has maximal interaction, now will having to change that A into X break some of those interactions? Yeah, because if A has maximal interaction, well, changing that into something else, the transition state must break some of those interactions. So now we have a problem, because we've got S bound, and S is supposed to get to X, but now in addition to the normal amount of energy that we have to put in, the activation energy, we also have to break those bonds that are being formed between E and S. Right? So it can't be that E binds S so good, and then magically makes the reaction proceed forward. So how can it lower the activation energy? It does have to, we're like skirting around it, right? Well, E can't bind the best to S, right? That can't be the maximal interaction. What would be the best maximal interaction such that we lower the activation energy? In other words, that we make X more stable.
The energy of the transition state after it binds the transition state is more stable.
Exactly, right? So when the transition state forms is when we get the maximal interaction between the enzyme and now the transition state, which used to be the substrate, right? So if an enzyme bound the substrate the best, well, that would be worse than nothing, because now we have to achieve the transition state and break the interaction with the enzyme. But if the enzyme can bind the substrate good enough, and then form maximal interactions when the transition state forms, well, now we formed bonds to the transition state, so that lowers the energy there, right? And this is how the activation energy is reduced in an enzyme catalytic reaction. And again, because the lower the activation energy, the faster the reaction, now we have an increased rate in our reaction. Right, now, enzymes and substrates form the enzyme-substrate complex, okay? Substrates are recognized and bind to the enzyme's active site, so just like we saw in receptors. Again, going back to that same example, the estrogen receptor has the amino acid in the correct position three-dimensionally with the right characteristics to make good interactions with estradiol in this case. In this case, for enzymes, it will have also an active site with residues in the correct three-dimensional position and with the correct characteristics to maximize the interactions with the transition state, not with the substrate. But again, because the substrate and the transition state look similar, we're still able to achieve some degree of specificity. All right? We have some evidence for the active site. It's kind of outdated in the book because, of course, there's an active site. We've had structural biology for a long time, so we've got the three-dimensional structure of hundreds of thousands of different proteins, and we see the active site and where the substrate fits in. But kinetically, we can also see the evidence for an active site in our velocity plot here. All right. So if we look at the reaction velocity, right? What is the velocity of a reaction dependent on? Right? Does anybody remember from everybody's favorite class, Gen Chem? What determines the velocity of a reaction? Right? Again, let's say that we have our A yields P. Okay. What determines the velocity of this reaction? Concentration of A. Is that it?
Activation energy.
No.
The rate constant.
The rate constant. In this case, the forward rate constant. You also have the reverse rate constant. So the velocity of that reaction is just V times Ka. So if we measure the reaction velocity versus substrate concentration, A, what we get is a straight line with a y-intercept of 0 and a slope of Kf, right? And this is just a line that goes off forever, right? Until we reach the limits of solubility, all right? But if we examine the same thing with an enzyme catalyzed reaction, what we see is that it stops being linear and instead has this hyperbolic plot, right? We've seen this hyperbolic plot before when we talked about fractional saturation. So we already have an idea of the kind of mathematics that we're going to encounter, all right? And here we have just an example of what an active site looked like. Again, you saw this with the estrogen receptor, so I'm not going to spend time on that. All right, features of the active site. Active site formed a pocket, okay, so just where the substrate is going to bind. So a very small volume of the protein. And what's the purpose of the rest of the enzyme then? It's just to position those amino acids in the correct three-dimensional way, right? Of course, there's other regulatory components, but by far, one of the most important things that the rest of the enzyme does, that's not the active site, is position those residues in the active site in the correct way so that the interactions are maximized when the transition state is achieved. They are microenvironments, so by varying the identity of the amino acids in the active site, okay, we can create an active site that is mostly polar, mostly non-polar, mostly negative. It is negative in certain places, right? This again helps to achieve specificity. Substrate bind the active site using multiple weak interactions. And specificity depends on the arrangement of residues in the active site. Now, we can think of, all right, substrate binding to enzyme as something like this, right? So this is a lock and key model, but again, this is not a good way to think about it. So this has been outdated. Why? Again, remember, if this were the case, well, now this fits like a lock into the key, so interactions are maximized here. So actually achieving the transition state from this point would be harder than achieving the transition state without an enzyme. Really what we have is something that looks like this, right? A substrate binding to the enzyme induces a change in the structure of an enzyme. Remember, proteins can be somewhat flexible, like we talked about in chapter 2. So we see that binding substrate can induce a change in the protein, and now that change in the protein allows for maximal interaction between the transition state and the substrate and the enzyme, not the substrate and the enzyme, right? Okay, so getting into Michaelis-Menten kinetics now, how can we characterize or quantify how much an enzyme catalyzes a reaction, right? And for that, we have to make a couple of assumptions just to make our life a little bit easier. All right, so let's take the reaction A to P again, right? So A yields P. The velocity is, of course, K.F times A, like we see on the bottom there. But the velocity we can also consider to be the amount of product being formed per time. Okay, so how much product is appearing per unit time. This is also the velocity. So both of these are equal to each other. This is what we call a first order reaction. Okay, so A yields B. There's no second substrate or anything like that. So it's just a line, we don't have to worry. We can have second order reactions. We have, for example, A plus B yields P. In this case, the velocity would be Kf times A times B, right? But what we see very often, most of the time, in fact, in physiologic anyway, is that usually A or B will be much less than the other. So let's take the example where B is much greater than A, right? So A is much less than B. What we can say is that the velocity is roughly equal then to K times A, right? Because B won't matter, right? B is essentially going to be constant, right? So we can ignore that completely. This we call a pseudo first order reaction. So even when we have a reaction that includes two substrates, right? We can usually just assume that it's going to be a pseudo first order reaction. The reason why we want to have a first order reaction is so that we can simplify our life a little bit. Right? So let's look at a hypothetical enzyme catalyzed reaction. We can say that it's enzyme plus substrate yields an enzyme substrate complex, which yields enzyme plus product. I've left out going from ES to EX double dagger, right? I've just left that out, but then we can think of it like this. E plus S yields ES, which yields E plus B. And we can say that each one of these has their own rate constant, right? So E plus S over the ES has a rate constant of K1. The reverse is K minus 1. Here we have K2, and here we have K minus 2, right? So here's our prototypical hypothetical reaction here. And what we want to study is the rates of the reaction. In other words, how much product is being formed per time, right? So what we can say is that the velocity of this overall reaction actually really has nothing to do with this right now. All we care about is this, right? Which is going to be what? K2 times ES, right? So that's going to be the velocity of the reaction because this is going to equal how much product is being formed per time, right? So there we go. Now, because we want to study D product per time, right, let's examine how much product is formed per time at different substrate concentrations, right? So that's that same chart that we had over here, right? So if we study, okay, the amount of product being formed per time, we see a series of graphs like this, all right? Series of graphs like we see right here. Eventually we reach equilibrium, all right? And what we see is that we start off with some really high values, some really high velocity, right? Notice what we're looking at there with the dotted line is the V naught, right? The initial velocity. Reason why it's a velocity is because it's a slope at that point, right? So it's just a derivative at that point. What's the slope? Well, it's just y over x, so it's product over time. So the slope of this line is the velocity, right? V naught, initially. And why do we want to look at the initial velocity, right? Why do we care? Well, again, it's going to make our lives easier, right? There will always be a reverse reaction, right? There will always be some P and enzyme coming together to make ES, right? Except for exactly at time equals 0, right? So if we have a beaker and we have enzyme and substrate at time equals 0, 0.00, right? We only have enzyme and substrate. Nothing is happening, right? So by looking at this kinetic graph on the last slide, okay, plotting that, finding a fit line, and then taking the derivative at t equals 0, we can find the initial velocity at t equals 0. Why do we care about that? Well, it's because at t equals 0, there is no p, right, to go backwards, right? So if we look at what velocity the reverse reaction would have, right, going from EP to ES, velocity reverse would equal k minus 2 times E times P. If this is 0, then velocity is 0, right? So we can ignore K2 completely, okay? So when we're looking at kinetics, we ignore, or K minus 2 rather, we can ignore K minus 2 completely because there is no product initially, right? So no product being formed initially. Now, if we, again, look at all of these kinetic plots, again, like we had on the last slide, right? So at S4, at S3, at S2, and S1, we'll see that they have different slopes, right, at time equals 0. Which means that if you notice, as we add more substrate, the initial velocity of our enzyme catalyzed reaction increases. And we can plot that here. So if we look at the top graph here, we have reaction velocity versus substrate concentration. You see that it also increases exponentially, right? Hyperbolically, right? So we get this kind of curve that we see at the bottom, right? And this makes sense, right? Because if we look at the initial velocity, Vf equals k times s, right? This going forward here. So if we add more s, then we should see an increase in the velocity, which we do. So what is this plot? Well, this plot is our Michaelis-Menten plot, reaction velocity versus substrate concentration. And to derive it, we have to make a second assumption, and that's that the amount of ES is constant. That means that ES is being broken down at the same rate that is being formed. We call this a steady state assumption, right? So the rate of breakdown of ES, breakdown equals the rate of formation of ES. And now we have everything that we need to derive an equation to tell us the velocity of an enzyme catalyzed reaction, right? So let's start off here, right? If we look, we have our E plus S yields ES yields E plus P. At that time equals 0, P equals 0, so we can ignore K minus 2 as we said already, and that the rate of breakdown of ES is equal to the rate of formation of ES. So let's start there, right? So we've got rid of K minus 2, okay? So the rate of formation of ES, well, how can ES be formed? Can E and S come together to make ES? Right, okay, so that reaction, K1 times E times S, right? So that's formation. Can E plus P come together to make ES? shaking your head. Why no?
There's no P.
Right, there's no P. So E can't come together with P if there's no P at time equals 0. So that's it. That's the rate of formation of ES. The rate of breakdown of ES, though, right, what can we say? Well, we can break down ES into either E plus P or E plus S, right? So what are those rates? Well, we have ES times K minus 1 plus ES times K2, right? So now we have our formation, which equals the rate of breakdown, right? So let's factor out the K's and get them all on the same side of the equal sign, right? So K minus 1 E S equals K1 minus 1 plus K2 times ES. We can say then that ES over ES equals K minus 1 plus K2 over K1. Right? So now we have all our rate constants on this side, all our concentrations on this side. We're going to call K minus 1 plus K2 over K1, that ratio of rate constants. We're going to call that our Km, all right? Our Michaelis constant. Every enzyme is going to have its own Michaelis constant that doesn't depend on enzyme concentration or substrate concentration because it's just a ratio of rate constants, which is characteristic of this combination of enzyme and substrate, right? So we have our Km. And what we can think of Km being is K1 plus K2, right? Which is breakdown over K1, which is formation. Breakdown over formation. So the lower the Km, we can say is that more ES forms that is broken down, right? So the lower the Km loosely, the higher or the lower the Kd, right? The stronger the association. It's not quite, and we'll do an example on that, right? So where are we? Okay, so let's solve now for ES. Instead of going through the board, let's just pick it up over here, right? So we have E times S over ES equals our Km. We solve for ES, so ES equals E times S over Km. The problem is, we don't know what E is. We don't know what ES is. Okay, so why is this a problem? Well, we don't know what ES is, but that's actually okay, because what we're trying to do is to figure out the velocity. And we know that the velocity is equal to K2 times ES, right? So keep that in mind as we continue here. So for now, let's solve for ES. Again, we don't know ET, but we do know that the total amount of enzyme we have, E total, must be equal to the amount of free enzyme that we have, E, plus the amount of enzyme that's in the enzyme substrate complex. So E total equals E plus ES. In other words, E total minus ES equals E, right? So ES equals E total minus ES, which is equal to free enzyme, times S over Km. Now do some algebra, right? So distribute out the S and we solve for ES. We get ES equals E total times S minus ES times S over Km. So move the Km on this side, right? Solve ES equals E total times S over S plus Km, right? Do you want to go through each individual step or are we good? Does that make sense? Don't waste too much time, right? So now we solve for ES. Why did we want to solve for ES? Because again, what we care about is